So as we move past related rates here, we're not going to go too far away from derivatives. We're going to be using them as much now as we ever have been, but always the first derivative. And we're going to use them to find extrema on an interval. So you know from Algebra 2 and earlier this year that we have two types of extrema. We have relative extrema and absolute extrema. Relative extrema, obviously, if you look at your graph here, is relative to the points both to the left of it and to the right of it. So this right here is a relative minimum, because relative to the points to the left and to the right of it, it is a minimum point. It also happens to be a maximum, or I'm sorry, not a maximum, an absolute minimum, because it's the absolute lowest point on this graph. As far as relative maximums, we don't have any here. This is the absolute maximum because it's the absolute highest point, but it's not the highest point relative to those to the left and to the right, simply because there are no points to the right of it. So this is an absolute maximum. This is an absolute minimum as well as a relative minimum. This doesn't really fit into either. It's not the absolute maximum point, not the absolute minimum point, and it's also not a minimum relative to these points on the left and these points on the right. So that's really nothing, and this one is nothing because it looks like it kind of wants to be a maximum, but it's obviously not the highest point because of this one, and there is no relativity to points to the left of it because the points to the left of it don't exist. So visually, that's what our extrema are as a reminder. And the most important point is that these occur when the slope is 0, when the slope does not exist, or it can happen at endpoints. Okay.
Oh, there she is. Yeah, she's right here.
What's up? Hold on one second. Okay, sorry about that. Small interruption. So on this first one, find the extrema of the function f of x equals 3x to the fourth minus 4x cubed along the closed interval. They obviously showed it to us, but we need to kind of show you algebraically how to find it. If something is a relative extrema in any way, the derivative needs to equal 0. Obviously, you can look at the relative one here and see why the slope is 0 right there. So the slope equaling 0 is going to help us find the relative and maybe the absolute. But the absolute could also be the endpoint, and you're not going to get a slope at an endpoint, right? Things are not differentiable at an endpoint. So when I write this critical points piece here, it's either when the derivative is 0 or does not exist, and then your absolute extrema may or may not would be at the endpoints, or could be at the endpoints. So we need to find all the places where the slope is 0 or the slope does not exist, and we need to find the points at the endpoint. So let's start with our derivative here. So if we take our function f prime of x equals 12x cubed minus 12x squared. Very simple power rule there. We want to know when this is undefined, does not exist, and that never happens, and also when this equals 0. So I'm going to set it equal to 0 and solve by factoring out of 12x squared. And we find that at x equals 0 and at x equals 1, there is a slope of 0. So if I kind of look at my points, my critical points are 0 comma something, 1 comma something, and also my endpoints. Now they gave you the interval, so if you didn't have the graph, you'd get your endpoint x coordinates from the fact that this is starting at -1 and it's ending at 2. And then I just want to find all these points. So if I plug in 0, I get 0. If I plug in 1, I get 3 minus 4 is -1. If I plug in -1, I get 3 plus 4 is 7. And if I plug in 2, I'm going to get 2 to the 4th power, 16. 16 times 3 is 48, minus 2 to the third power is 8. 8 times 4 is 32. So 48 minus 32 is 16. So here are all my critical points and my potential, in my endpoints that are potential absolutes. So if I, first of all, want to find my absolutes, I just want my absolute highest y-coordinate. So this is going to be my absolute max, and obviously that lines up with the picture. And the lowest point is -1, and that's an absolute min. Okay, now the -1,7 is obviously an endpoint, so there is no chance for a relative there, and it's obviously not our absolute anything either. At 0, 0, where we have a slope of 0, 0 there, or of 0 there, it evens out, but then it continues down. So because it has a slope of 0, there's a potential that it could have turned around. But the slope prior to 0 is negative, and the slope after 0 is negative. But obviously we're not going to have the visual every time. So how could we figure out that the slope is negative to the left and also still a negative to the right? So if it continues to decrease and it just hits a slope of 0 for an instant momentarily, but then it continues to decrease, how would we know that? So at 0, 0, we would want to check and see what is the derivative, aka what is the slope just prior to 0. So if I were to plug in -0.5 to my derivative here, and I picked the factored version. If I plug in -0.5, I'm going to get a positive times a negative, which tells me that my overall derivative will be negative prior to 0. If I plug in +0.5, my derivative will be a positive times a negative, which is still a negative. So that has remained a negative slope, which means it would not be a relative anything. As for the other critical point that was not an endpoint, this 1, -1, obviously we checked the slope slightly to the left as being negative. If you were to plug in the slopes, or a number slightly to the right to calculate the slope here, like at 1.5, if I plug in 1.5, I'm going to get a positive times a positive. So that's going to give me a positive slope there, which obviously if the slope has gone from a negative on one side to a positive on another, it obviously had to turn around at some point. So this absolute minimum is also a relative minimum. Okay, so that's kind of the synopsis of everything here going on. And sometimes when you mix absolute and relative, it gets a little confusing. But that's what we're going to be exploring more in depth over the next few lessons here. And really the whole chapter is kind of going to take closer looks at this. So on this first example here, on the bottom where we're just finding the value of the derivative, if it exists, at each indicated extremum. So we're finding the value of the derivative there. Now, we know if that's a relative extreme point, it should be 0, but we're just kind of confirming that. So if we take the derivative of our function, we need the product rule. If you want to rewrite this, you can rewrite it as -3x times x plus 1 to the 1/2. So if we do the first times the derivative of the second, which would be a power, times the derivative of what's inside, which is just 1. So it's a power in a chain. So first times derivative of the second, plus our second, times the derivative of the first. And we want to clean that up. So it's going to be -3x over 2 root x plus 1 minus 3 root x plus 1. And we just want to evaluate that at the point. So we're just going to plug in a -2/3. So -3 times -2/3. Your 3's are going to cancel, your negatives are going to cancel. You'll just get 2 over -2/3 plus 1 is negative 2/3 plus 3/3, which is 1/3. So that'll be 2 root 1/3 there, minus 3 times root, and again, negative 2/3 plus 3/3 is 1/3. So these 2's will cancel, and if I get a common denominator, put this over root 1/3, give this a root 1/3, it's going to be 1 over root 1/3, minus this times this will be 1/3, 3 times the 1/3 will be 1 over the root 1/3, and we confirm that our derivative at that point is 0. So it's just sort of a confirmation that our relative maximum, and also it happens to be our absolute maximum here, but the relative maximum in particular has a slope of 0. This one's a little tricky because we don't know how to find the derivative of this using our shortcuts. This is one of those instances where we cannot use our shortcuts. So we have to remind ourselves of the alternate form of the derivative, which was, you can find the derivative of it at any given c value by taking the limit as x approaches c of f of x minus f of c all over x minus c. And so for this particular problem, we're trying to find the derivative at an x value, or in this case, a c value of 0. So we would do the derivative at 0 equals the limit as x approaches 0 of f of x, which is 4 minus the absolute value of x, minus f of c, and c is 0 here, so f of 0 would give me 4 minus 0, which is 4, all over x minus my c value of 0. So when I clean this up, on top the 4 minus the 4 is going to cancel, so it's going to be negative absolute value of x over x, which is a jump function. So the limit of a jump function, you plug in 0 over 0, it gives you the indeterminate case for your limit, but we know this to be one of those jump functions. So as I approach 0 from the left, I'm at 1. As I approach 0 from the right, I'm at negative 1. And so the limit does not exist here. So if the limit does not exist for this, then the derivative at 0 does not exist. And that should make sense because we've come to a sharp point at that relative maximum. So just kind of showing you that if it's a relative max or min, the derivative is either 0, like we confirmed over here at this relative max, or does not exist, that we confirmed over here at this relative max. Critical numbers. Again, critical numbers are where the derivative equals 0 or the derivative is undefined. So we want to find the derivative. Going to need the quotient rule. So our bottom times derivative of the top minus our top times derivative of the bottom all over bottom squared. Clean that up. We're going to get 4x squared plus 4 minus 8x squared. Clean that up one step further. We get negative 4x squared plus 4. Okay, again, critical points are going to come from where the numerator is 0. So I would set this equal to 0 and solve. Subtract 4. Divide by negative 4. Square root both sides. So x equals plus or minus 1. So those are critical numbers, critical x coordinates. If we wanted the full critical point, we would plug each of those back into the original to get the y coordinates. So it would be 1 comma something and then negative 1 comma something. And then when your denominator equals 0, you'd have it undefined. So x squared plus 1 squared would equal 0. This is actually never going to happen. Obviously, if we square root both sides, we get x squared plus 1 equals 0 still. Then you're going to get x squared equals negative 1, which is never going to happen. So we have no critical points coming from undefined slopes. If we want to go just a bit further and actually find those points, like I said, we would just plug 1 into the original, and I'll do that, erase that. If we plug 1 into the original, our actual critical point is at 1, 2. And if I plug negative 1 back into the original, I get negative 1, negative 2. So those are our critical numbers, critical points. Those are our potential relative max, relative min, absolute max, absolute min. That doesn't mean they necessarily are. They are just our critical ones, and they could be. So if we take a minute just to wrap our head around this visually, what's happening here. This graph is 4x divided by x squared plus 1. And once we look at the graph, we can see the point at 1, 2, it's an absolute max, and it also happens to be a relative maximum. And right down here, we have negative 1, negative 2, which is a relative minimum as well as an absolute minimum. So we can see that our points actually came up with something good and legit. All right, I'm just going to jump to one of these below, locating the absolute extrema. We can go back up to that other one in a minute, but locating the absolute extrema on the closed interval. So, again, when it's a closed interval, your absolute extrema could happen at one of the endpoints. So immediately our critical points should include those endpoints, 0, something, and 4, something. And on top of that, we may get a couple more possibilities based on where this derivative equals 0 or equals undefined. So if I just plug in 0, I get 0, 0. That's one potential critical point. And if I plug in 4, I'm going to get 64 minus 48. And 64 minus 48 will give me 16 if I'm being lazy. And then we also need to find where our derivative equals 0 or is undefined. So there's my derivative. It's never going to be undefined, so we only need to worry about where it equals 0. So that could be at positive 2 or negative 2. So we're going to find the rest of those points. So if we plug in 2, we're going to get 8 minus 24, negative 16. And if we plug in negative 2, we're going to get negative 8 plus 24. So we have a couple issues here. First of all, they're only asking for the absolute. The second piece, though, is they only want it in this interval. So they're only looking at this graph from 0 to 4. One of our points is not in that interval, and it's this last one. So yes, the derivative of this function, yes, the slope of this function equals 0 at negative 2, but we're not looking at when x is negative 2. So that is rejected because it's out of interval. And then since it's only looking for absolute maxes or absolute mins, I don't really need to go into the relative piece right now. I can just pick the highest number as my absolute max, and my lowest number is my absolute min. And then this might be something, but I'm not sure exact. It's not an absolute max or min. So if I check my graph just to make sense of the whole thing. And I only actually want to look at this from 0 to 4. So I'll just go 0 to 4. And my y coordinates go up to 16, so I'm going to go negative 20 to 20. So here we are from 0 to 4. And now it makes sense. Our absolute maximum point is at one of the endpoints. That's 416. Got that. And my absolute minimum was actually at one of the places which had a slope of 0, so 2, negative 16. This endpoint was nothing, happened to not be an absolute of any sort. Remember, endpoints can never be relatives, but it may or may not be an absolute, and this 0, 0 was not an absolute anything. but the other endpoint was one of our absolutes. Okay? So I'll do the rest of the examples on here. They get a little bit more challenging just because the derivatives are more challenging, but we'll go back up to number 2 here. And again, this is back to finding just critical numbers. So my derivative, the derivative of secant is secant tan, plus the derivative of tangent is secant squared. Okay? Now if I clean this up, I can factor out a secant theta. And again, I'm looking for where this equals 0 or where this is undefined. Now, to tee it up and set each piece equal to 0, the secant of theta, remember because that's 1 over the cosine of theta, that will never equal 0. That's never going to happen. But this one could equal 0. So I'm gonna first change, rather than just set it equal to 0, I'm also going to change it into sines and cosines at the time. So that's the tangent is going to become sine over cosine. The secant is 1 over cosine theta, and I'm waiting for this to equal 0. Now they already have common denominators, which is nice. So I'm looking for when this equals 0, and it will equal 0 when the numerator is 0. So I'm going to set that equal to 0. 2 sine theta plus 1 equaling 0 is going to be a sine theta equaling negative 1/2. And we're only in the interval from 0 to 2 pi. So sine equals 1/2 when the angle is pi over 6. But negative 1/2 would be the third and fourth quadrant versions of that for sine. So this would be 6 pi over 6, so that would be 7 pi over 6. And this would be 11 pi over 6. So that's going to be where my slope is 0. And my slope will be undefined if my denominator is 0. So if my denominator is 0, theta would have to be pi over 2 or 3 pi over 2. But since cosine of theta equals 0 when theta is pi over 2 or 3 pi over 2, we actually don't need to worry about these two being critical points, because if you go back into your original, there are no points even on the function. The entire function is undefined at pi over 2 and 3 pi over 2 because the tangent is undefined at those points. So if these points don't even lie on the original function, then there's no way they could be critical points. And so therefore our critical points, our critical numbers, is all this really asked for, was 7 pi over 6 and 11 pi over 6. Okay, if we jump down to number 2 on the bottom, we can take the derivative. Well, we'll start actually with my critical endpoints. So 3 comma something and 5 comma something. 3 plugged in will give us 3 over 1, which is 3. 5 plugged in will give us 5/3. Okay, and as far as the derivative, so h prime of t equals bottom times derivative of the top is 1 minus top times derivative of the bottom is 1 all over bottom squared. That's going to be t minus 2 minus t up top. Your t's are going to cancel, and your derivative is just negative 2 over t minus 2 squared. So when will this equal 0? Never. When will it be undefined? At 2. But 2 is not in our interval. So 2 is not a critical point within this interval. So that's it. So this is our, what's the higher number? 5/3 or 3. This is our absolute max. And this is our absolute min. For visual confirmation, so we can wrap our head around what's happening here, we want to look at this from 3 to 5. Negative 5 to 5 should work fine. There's our graph. So the absolute maximum point is right where it starts at 3, 3. and our absolute minimum point is right where it ends at 5 5/3. Number 3, again, critical points. Start with your endpoints, negative pi over 6 and pi over 3. So the secant of negative pi over 6, if you know your trig values, should be 2 root 3 over 3. Pi over 3, the secant of pi over 3 is the reciprocal of the cosine of pi over 3. So 1/2, the reciprocal of that would be 2. And then we have to find the rest of our critical points from the derivative. So g prime of x equals secant x tan x. And we want to find out when this is equal to 0. So we set it equal to 0, and I would probably make this 1 over cosine x times the tangent of x. When you tee it up, this will never equal 0. But the tangent of x, and remember we're only in this interval from negative pi over 6 to pi over 3. So the tangent, that's just so you have a clear sight, negative pi over 6 to pi over 3. We're only staying in this interval. So when is tangent 0? Well, at 0. So x equals 0. So we have another possible critical point there. And 0, if you plug in, the secant of 0 is 1. So if you look at your points, you would need a calculator to come up with the decimal to that so that you could compare it with everything else. That's 1.15-ish. So the absolute max is the highest point, and the lowest point is your absolute min. Okay, last one here. Critical points. -1 comma something and 3 comma something. That's going to hit up our endpoints. If you plug in -1, you're going to get 1 minus 2, which is -1, minus the cosine of -1. This is going to need a calculator. When you plug in 3, you're going to get 9 minus 2, which is 7, minus the cosine of 3. So I've already taken the liberty of coming up with those decimals, -1.5 and 8 is my y-coordinate there, approximately 8. And then the rest of our critical points is going to come from the derivative. Derivative of x squared is 2x, the derivative of -2 is nothing, and the derivative of cosine is negative sign, so minus a negative sign is going to turn that into plus sine x. And I want where this equals 0. It's never going to be undefined. I want where it equals 0. So when will 2x equal negative sine x? And this is going to take some thinking here. So the sine of 0 is 0. So 0 would work. You plug in 0, you're going to get 0. So 0 would be one critical point. When else does the sine of x, you could go to like pi over 6. That's sine of pi over 6 is going to be 1/2, but when you plug in pi over 6 on the left, you're going to get pi over 3. Does pi over 3 equal -1/2? No. So you could plug in all your angles, but we're really only going from -1 to 3, so that's tricky. You could plug in your whole numbers, and the only one in that interval that's going to work is 0. So if I know it's 0, if I plug 0 back in up here, 0 minus 2 is -2, minus the cosine of 0 is 1. So -2 minus 1 is -3. So if you compare your y-coordinates, this is your max, and this is your min. Min, and that's your max. Alright, so the homework at the bottom, page 169, I obviously cut down. That's 1s, 5s, and 9s only to cut down for tonight's homework. If you have questions on any of these examples, have those ready for class tomorrow, and then obviously any questions on your homework.